please try and look at Web Campus, right? Look at Web Campus. Make sure that the tallying and everything was done right, right? The final grade book for the class is on WebAssign, but you see your score for the exam also on Canvas, right? But please make sure everything was right. Looking at the comments, why I deducted points, if I made a comment and then you had it there and then I still happen to deduct, still check it out, right? And I'll be more than happy to correct the errors, right? So please let me know as soon as possible, right? Regarding that. Also, please, I don't know if Jesus and Cole are here. If you are, please check for Jesus, check the chat. I just sent you something. And then for Cole, check your Canvas notifications, right? So that's all I'll say on that. So please check that and try and get to me as soon as possible. Okay, so any comments from you regarding the exam? Do you have any questions, any concerns, something that you think we can do to improve it, or the structure is fine, no problems? I mean, the first time is always something because you don't know what to expect. That's why I was like, I generated the structure for you to view earlier on. Yeah, but overall it went okay. You guys did great. And I liked a lot how you like uploaded the files and stuff. A lot of you did very, very like awesome jobs. Okay. Any questions about the exam? Any comments? Okay, the time. Okay, the time. Okay, Ashley. Okay, so a little short on the time. Okay, let me see. Yeah, so that's why everything was like in a hurry. There's just 50 minutes, and I gave an extra 10 minutes for the upload, right? Let me see. Going forward. Yeah, okay, yeah. I mean, I had that in mind because the time it's 15 minutes and then 10 minutes to submit. But still, yeah, okay, going forward, I'll still consider that and see. Yeah, I usually grade my exams very quickly. I mean, if it's there, why sit on it? I don't like to wait on a job. Like, just get it done and then we can move on. We close that page, we move on to the next. And even this one is online, so the grading takes some time. But if it had been in class, yeah, so just grade it quickly. Let's get on to the next one. You're welcome. Okay, didn't know about the 10 minutes. That fixed. Oh, okay, yeah. So you are supposed to be able to work everything in 50 minutes, right? Because that's the class time. So supposing in a class setting scenario, right, the 50 minutes is what you use to solve it. And then when you are done, what do? You turn it in as you leave the class. And you turn it in after the 50 minutes. That's why I gave extra 10 minutes for you to upload. That's why on Canvas, you see the time was 60 minutes, right? So like 50 minutes to solve, WebAssign and the written. And then within that 10 minutes, you can take the photos and upload before the time expires. So that was the plan. So I think, yeah. So for the timing, maybe it's because you didn't see that, right? But yeah, that's the whole thing with, yeah. So just next time, just note that, right? 15 minutes to solve, you have 10 minutes to upload. That's why I said it with like, the exam material, I said it for like about closely 40 minutes to solve everything, right? 40 minutes. And then you have like 10 minutes and some extra 10. So that's like how I program it. Yeah. So next time you'll be fine. I think with this instruction, now that you know how to go away, you'll be fine. Yeah. Okay, I'll go ahead. Yeah. Jesus, thank you. Thank you for replying. I don't know. Is everyone set? Yeah, it's okay. It's public, right? Everyone can comment publicly. I'm getting only private message. That's why I'm concerned. Let me see. Okay, so we are done. Okay, so please, I think Jesus has addressed this. So Cole Harris, right? Cole, if you are here, please try and check your web campus as soon as possible. And please make sure you check, make sure there are no errors, right? Make sure there are no errors. I've also posted the solutions, by the way, to the written part. So compare, right? I'm more than happy. I mean, people can make, I'm human. I could make maybe tallying errors or something, right? So just check it out. I try as best as possible to give my best to give you the best outcome. But then still check it, right? Please check it. Make sure everything checks out just fine. Okay, so that's the comment on the exam. Yeah, you're welcome, guys. You're welcome. You did awesome. Okay, so now let's move on. If there are no questions or comments, then let's move on. Or any other questions? Or did I miss something? Okay, I think I didn't miss anything. But if I miss anything in the chat, do feel free to draw my attention. Okay, so now let's go. So last time we were at 2.8. Share. Please, I'm sharing my desktop. If you can't see, do let me know. F5. No. Shift function. Okay. So the last thing that we did, we looked at this, right? We looked at using the definition of derivative to solve this, right? So we got this, and we wrapped this up, and then we're here, other notations. So last week we introduced like the definition of a derivative. And then it turns out that for this definition of a derivative, there are different notations that we are going to use to represent this. We said that suppose you have a function f of x, right? And then the independent variable is x, and then the dependent variable is y. Now, if you have this function expressed in terms of x, then the derivative can be defined as follows. So these are the notation that represent the derivative. So you have f prime of x, right? This is what we have already seen. We've seen this before, right? So this is the derivative of f of x at x, right? Now the same f prime of x can be written as y prime, right? So y, in the sense that f of x is just function notation. So if we have f prime of x, then we have y prime of x, kind of like that. That's straightforward. And then this same thing can also be written as this. So you have dy over dx, right? dy over dx, right? So that's what you see here. Now this is the same as the f prime of s, or the same as y prime. So if a question should ask you about this, to know that it's not anything new, it's the same as this. You can also have d over ds of, no, okay, let me say df over dx. df over dx is also the same thing, in a sense that this f represents the function here, and then dx down here. Okay. Now, what is down here represents you have the independent variable x here, and then d. So it's always d and then the independent variable. So if a function is expressed in terms of x, it's just d of the independent variable. So if it's expressed in terms of t, then the denominator will be dt, right? If it's expressed in terms of u, then the denominator will be du, and so on and so forth. Now, this same thing can be written as d over dx and then f of x. Also the same thing, right? The same notation. Now, the last two, we are not going to use them, right? In this class, we'll be using this. So I'll be, based on convenience, I'll be interchanging between these 1, 2, 3, 5, right? So we will use this, use these in class, in this class. Now, this d over ds thing is called a differentiation operator. And then the capital D, as I said, we won't be using the capital D. You'll be using d over dx, right? So this is a differentiation operator, right? And we always, when it's attached to a function, it just means that you are about to take the derivative of that function, right? So if I have, say, s squared, this is the function f of x, right? So if I want f prime of x, it's just writing this as what? D over dx s squared, something like so. So as long as you see this d over ds attached to the s squared, that means you're about to take the derivative. Please, are you okay with the notation? Any questions on this? Okay. Anybody needs time here? Okay. So now, now this symbol that you see here was introduced by a man called Leibniz. Now, the whole idea of calculus, even though people develop some like bits of it, the people who are credited with the calculus are two, Sir Isaac Newton and then Gottfried Leibniz. Now, Sir Isaac Newton developed his ideas on calculus during the Great Plague. So it's similar to what we have like in coronavirus in this modern era. So when they had this thing came up, there was the plague during their time, and their schools closed down. So they had to go home. And when he was staying away, he developed some of these ideas for the calculus, right? He developed his ideas, but he didn't publish his ideas. He said that he thought that it might lead to controversy, so he kept it to himself. And then this other man, Gottfried Leibniz, also developed his. And then in the long run, there was like a fight over who is supposed to receive the credit for developing calculus between Sir Isaac Newton and Gottfried Leibniz. But in the long run, they saw that each person developed this separately, right? Yeah. Isaac Newton developed this first, but he didn't publish. And then Leibniz also got to develop it. So you see some of these names come up, right? So Leibniz and Newton's law of cooling and stuff. So those are the two people who are credited. Of course, several other works were done by other people, like a bit of it were done by other people, which you get to learn about them with time. Yeah, so that's what this name is standing for. One of the people credited with developing calculus. So Gottfried Leibniz. So he brought this notation, the dy over dx, right? And we should not regard this as a ratio, right? I mean, for the time being, it is simply a symbol for this. Okay, so now dy over dx is expressed with a rate of change. Is also, you know that the rate of change formula is a limit as the delta x approaches zero of changing y over changing x, right? So this is the same as dy over dx, right? So this is just notation. Please, any questions here? Anybody needs time here? Okay, now we have f prime of x, right? But when we started this whole integration thing, we were trying to find f prime of a. So the question is, how do you get f prime of a when you have f prime of s? Well, it's just f prime of s evaluated at a, right? F prime of s is like more general x. So when you have a number a and you want to find f prime of a, you just plug it in f prime of x. So now that we know that the notation for f prime is dy over dx, right? If you want to find f prime of a, then we have this vertical line here and you just say s equal to a. So this is the same as what f prime of a. Or you can also have this kind of like the end of a square bracket and then s equal to a. For each of these, the notation is just for f prime of a. That means the derivative evaluated at what? At e. So that's it. So if you encounter this, that's what it means. Please, are you okay with this? Any questions? Okay. Now, if the f prime of a exists, right? Don't forget that the f prime of a is a limit. If that limit exists, then we say that the function is differentiable at that e, right? We say that the function is differentiable. So one other thing is, if a function is differentiable on an open interval, then it is also differentiable at every number in that interval, right? So that means the limit exists for that special f prime of a. Please, are you okay with this? So that's the new term, differentiable. So for now, if I say differentiable, you know that that special limit exists. Anybody needs time here? Any questions on the notation and or the definition? Okay, so now let's move on. So let's investigate this function. So where is this function differentiable? Where is it differentiable? In other words, if you're trying to find f prime of s for any of the x's, is the limit going to exist for all the x's? Well, to investigate that, the solution is on the PowerPoint, but let's do that on the side, right? So this 2.8, example 5. I'm sharing the whiteboard now. If you can't see, do let me know. Okay, so now don't forget that the absolute value of x function is a piecewise function. It's going to be x if the x is positive. It's going to be 0 if x is 0. And it's going to be what? Negative x if x is negative. So what you're going to do is we are going to investigate f prime of x for these x's, when the x is positive, when the x is 0, and when the x is negative, and see if the limit will exist, right? So let's start with when x is equal to, when s is positive. Let's start with this. So when s is positive, let's see if this limit will exist. So what's f prime of s? In general, f prime of s is the limit as h approaches 0. So that's why I said this formula is very important. We use this to obtain all the other kinds of formulas you meet, right? So limit as h approaches 0, f of s plus h minus f of x all over h, right? So let's try and see, when x is positive, is this limit going to exist? Or is the function differentiable when the s is positive? So we get f prime of s equal to the limit as h approaches 0. What is f prime of f of s plus h? Well, we know that f of x is absolute value of x. So f of s plus h is going to be what? Can anyone please help me with that? What is f of s plus h going to be? Okay, close. I have s plus h, close. Probably that one is like far ahead. You're giving me the answer far ahead. But please, let's start from like the absolute value of x. You get to the, yeah, that's like ahead. Yeah, so that's correct or the same. Perfect. Thank you. Yeah. So it's going to be absolute value of s plus h, right? Because if f of s is absolute value of s, then f of s plus h is the absolute value of s plus h. Okay. So the next part is what? F of x. F of x is just absolute value of s. So let's just write that. And then all over h, like so. Now, because x is positive, and then the h is approaching 0, that means that this absolute value of h here, let me do a side, please wait, let me write something on the side here. Something to note. Let's try and get the absolute value of s plus h. So if absolute value of s is x, if s is positive and 0, if s is 0, and then negative s if s is negative, then that means absolute value of s plus h will also be s plus h if the s plus h is positive. It will be what? 0 if the s plus h is equal to 0. And then it will be negative s plus h if the s plus h is what? Is negative. So please note this. Right. So if we have all of those, then the f prime of x will be equal to what? So we have limit as h approaches 0. Now for absolute value of x, because the h is approaching 0 and the x is positive, don't forget that we are looking at the case where it's positive. That means x is positive and the h is approaching 0. So that means this whole thing is what? Is positive. The s plus h is positive for that condition, right? So the absolute value of s plus h becomes s plus h, which is the answer that I think Donovan gave me. Yeah, so that's correct. And then the absolute value of s, when s is positive, absolute value of s is x, right? So that means we have what? Minus x, and then all over h, right? So that means this is going to become, you have limit as h approaches 0 of the x's cancel out, and we have h over h, which also cancel out to give us 1. Now the limit of a constant is a constant, so that's 1. So this limit exists, right? The limit exists. So that means we can conclude that whenever s is positive, the function absolute value of s is differentiable. Please, are you okay? That's the conclusion. So f of s is differentiable for x positive. Please, are you okay with this? Any questions here? How did I get the 1? Okay, so I got, I am here. Let me try and highlight this. So here, up to this point, right? Please, I hope you understand up to this point, right? You understand up to that point? Do you understand up to the, yeah, okay, cool. So if you understand that one, then it's just the x here minus the x here. So that will go to 0. And then we have h over h, right? So h over h will cancel out. So h over, I'm coming, give me a sec. H over h will cancel out, right? After the s is subtract. I still see something in the chat. Yeah, h over h is 1. Yeah, perfect. Yeah, so that's how come we got a 1. Okay. Please, any other questions here? Anybody needs time here? Okay, then let's move on. So we know that the function is going to be differentiable. The absolute value of s function is differentiable when the s is positive. What about when x is negative? When s is negative, right? So let's investigate that. So we have f prime of s equal to limit as h approaches 0, f of s plus h minus f of x all over h, right? So the same thing, limit as h approaches 0. Since f of s is absolute value of s, f of s plus h will be absolute value of s plus h. And then minus what? Absolute value of x all over h. Now, because the s is negative and h is approaching 0, this s plus h will be what? Will be negative. Since the s is negative and h is approaching 0, so the s plus h will be negative. So that means that for the absolute value of h, we will have to represent that with what? Negative into parentheses s plus h. Right, so we have limit as h approaches 0, and then negative s plus h, like so. And then minus, for absolute value of x, right? When the s is negative, the absolute value of s is just negative x. So we can just put that one also in there, negative x, and then all over h. So that'll give us limit as h approaches 0. And then we have negative x minus h, and then plus x over h. So similar to what we had for the previous one, the s's will cancel out, And then we have negative h over h, which will give us limit as h approaches 0 of -1. And then the limit of a constant is a constant. So that means for this two, we had -1, right? So the limit exists. So the function is also differentiable. Absolute value of s function is differentiable when the x is negative. Please, are you okay with this? So limit exists. So that means the function is differentiable. Please, do you have any questions here? Okay, now let's investigate the last piece of this piecewise function, which is when the x is 0. So when x is 0, so let's check that one and see what's happening. So when x is 0, f prime of x is same definition, right? It's limit as h approaches 0 of f of s plus h minus f of x minus f of x all over h, right? So if x is 0, then we are essentially looking for f prime of 0. Oh, why are we using a piecewise? Okay, so we are using a piecewise because the question is asking about absolute value of s, which is a piecewise function, right? So we have different pieces where the s is positive, when the s is 0, and when the s is negative. That's why we're doing it piece by piece. It's because of the question that we got. Please, are you okay on that? Okay, cool. So now let's continue with s equal to 0. So that one is just limit as h approaches 0. And this will be f of what? 0 plus h minus f of 0 all over h. So let's try and evaluate these ones. So limit as h approaches 0. The f of 0 plus h is just f of h. So if the f of x is absolute value of s, what is f of 0 plus h? Can anyone please help me with that? What is f of 0 plus h? What is f of 0 plus h? Anybody?
0.
0? Okay, close. Please look at it again. Try again and see. Close. Yes, f of h. What is f of h? If f of s is absolute value of x, what is f of h? Close. Okay, maybe let me write it here, like so. If f of x is absolute value of x, what is f of s? What is f of h?
Absolute value of h.
Perfect. Thank you. Yeah, and tailor to, yeah. So perfect. It's absolute value of h, right? So it's absolute value of h. So that means this one will be absolute value of h minus what? This f of 0 will be what? What is f of 0 if f of s is absolute value of x? Anybody? 0. Perfect. Because for f of 0, you are just replacing the x with 0. So you end up with absolute value of 0. Absolute value of 0 is 0. And then all over h. Please, I hope you're okay with that. So that leads to this, h approaching 0 of absolute value of h over h. Now, unlike the previous cases for positive and negative, where we could cancel out the h, this one we can't cancel out the h. We can't, right? We can't cancel out an h. We have to figure out to say, bring out the h, right? Okay, so let's try and find this limit. Now, the first thing you try here is to plug in. If you plug in, you're getting 0 over 0, right? And this is a general limit, right? It's two-sided. And then when you plug in, you're getting 0 over 0. That means you are stuck. So what can you do to get this limit, the general limit? Well, then the strategy will be what? To do the one-sided limit, right? Whenever you are stuck checking the general limit, try and do one-sided. But I'll have to move to the next slide. So do let me know if you need more time here. Okay, so now let's look at the one-sided. So let's check. So you're trying to find limit as h approaches 0 of absolute value of h over h, and we are stuck, right? So we try the one-sided. So let's do limit h approaching 0 from the right of absolute value of h over h. Now, if you're looking at limit as h approaches 0 from the right, then don't forget that for absolute value of h function, it's also similar to the absolute value of x. It's the same thing, right? It's just the h, the x is replaced with h. So that one will also be h if the h is positive. It will be 0 if the h is 0, and then it will be negative h if the h is negative, right? Now, if you're approaching 0 from the right, then that means that the h is taking on very, very small positive numbers. It's taking on very small positive numbers, but it's still positive. So that means that the absolute value of h can just be replaced with what? With h, and then over h. And then when we get here, we can now cancel out. So that'll give us limit as h approaches 0 from the right of 1, and that is 1. Right, so from the right, you are getting 1. Now, what about from the left? So from the left of 0, right, the absolute value of h is going to be negative h if the h is negative. Now, if you're approaching 0 from the left, then the h is taking on negative numbers. So that means that this one, absolute value of h, is going to be what? Negative h over h. And then these will cancel out, giving us what? Negative 1. So that means that one is 1. Yeah, sorry, negative 1. Now, you are trying to find a general limit, but the one-sided limits are not agreeing on a single answer. So that means what? The f prime of 0, which is the limit as h approaches 0 of absolute value of h over h, is what? It's DNE. It does not exist. Now, because it does not exist, and we say that a function is differentiable if the limit exists, that means that the function is not differentiable at 0. F is not differentiable at 0 because the limit does not exist. That means we can't find the slope of the tangent line at that 0, at 0 on the absolute value of x. Please, are you okay with this? Okay, now I'm not going to ask you to prove any of this, but we are doing this to illustrate something, which you'll see very soon. But to show you that I need to move on to the PowerPoint, so please do let me know if you need more time here, so that we see what is the characteristic at 0, what is happening at 0. Okay, so no one needs time. So this one is just going to give us nice notes of how it's computing everything. When the s is 0, we've already done this, we got 1. So the function is differentiable for s positive. When the s is negative, we get negative 1. So the function is also differentiable when the s is negative. The issue is when x is 0, right? So for that one, you see that the limit does not exist, right? The limit does not exist. That means the function is differentiable at all except 0. Now, that means that the f prime function is just going to be 1 if s is positive and negative 1 if s is negative. Now, when you are graphing this, you see that the 1 is a constant, right? So for s positive, it's always 1. It's a horizontal line, right? This is y equal to 1, and this is y equal to negative 1. So this is a horizontal line, that's a horizontal line. But at 0, you see a point tool here. You see a point tool. Now, you can just get this graph from this piecewise function, but the most important point I want to put across is this characteristic. So let's look at the original function. This is f of x equal to absolute value of x. So this is what I want to talk about, right? So for this one, let's use the technique that we learned in the previous session, like in this session, like earlier on, how to get the derivative graph from the original graph. So suppose you want to get the graph of f prime from this graph, right? Then you see that if you should put your ruler on this side and check the slope of the tangent line, the slope of the tangent line at every point on this curve, on this left, right, will be the same. It's the same slope, right? Which we already computed to be what? Negative 1. But when you get to this point, because of its sharpness, it's very sharp. So the question is, how will you get the slope? It can't be this. Like when we have the curve, right? When we had the curve, it was a horizontal slope. But this one, because it's sharp, you can't tell whether the slope is like so, like this, or like so. So that's why the slope is undefined there. In other words, the function is not differentiable there. So for now, if you see any graph, right, and then it has a sharp point, then that means that the limit, the derivative, the limit that involves the derivative will not exist at that point. So the function is never differentiable at a sharp corner. Right, so that's the conclusion we are making from here, right? That's why we went through all the proofs. Please, any questions here? Are you okay with this? Okay. So Now, let's look at, let's try and distinguish between this differentiability and continuity. Now, we learned about continuity in 2.5, right? Now, we've added some new knowledge, the differentiability. Now, it happens that it turns out that if a function is differentiable at a point A, then it has to be continuous at a point A. But the converse is not true. The fact that the function is continuous at A doesn't mean it's differentiable at A. And this is a very good example to see, right? The absolute value of x. The absolute value of x is continuous at 0, because at 0, the limit as you approach 0 will be 0. And then the normal limit as you approach 0 will be 0. And then, what do you call it? The function evaluated at 0 is also 0. So the limit and then the function value are the same at 0. So that means the function is continuous. But as we just saw, the function is not differentiable. Please, are you okay? So if a function is differentiable at A, then it has to be continuous. But the reverse is not true, right? So we use this property later on in, I think, somewhere chapter 4. Please, any questions here? Okay. So these are just definitions and building blocks. Now, we just learned one way where a function can be, a function may not be differentiable. Let's look at other ways where the function can also fail to be differentiable. Now, there are 3 ways that you're going to see for this course, right? So we just saw that for absolute value of s, the function is not going to be differentiable at 0. Why? Because there's a sharp corner there, right? So in general, if you see a sharp corner, a function has a sharp corner at a point, or there is a kink at that point, then the function is not going to be differentiable there. You see, the function is not going to be differentiable there. Okay, so that's one way. So when you're graphing or you see a graph and you see a sharp corner, then the function is not going to be differentiable. In other words, when you get to that point, there'll be a punch tool on the derivative graph. Okay, now let's look at another way. Another way is if the function is discontinuous, right? If a function is discontinuous at A, then the function is also not differentiable at A, right? So if a function is discontinuous, the function is not differentiable. And then the last part is, do you remember that the slope of a vertical line is undefined? The slope of a vertical line is undefined. That means that if you have a graph, right? If you're trying to graph something and it looks like something like so, a function like so, and you get to say a point like here, and you're trying to find the slope of the tangent, then that means that the tangent line will have will be vertical. So that means its slope is undefined, right? That's why the derivative for where a point A where there is a vertical tangent is also what? Not differentiable, right? A function not differentiable at such a place because the slope is what? Is undefined. So those are the 3 cases. I think they summarized everything here. Okay, so this is the first case. No, wait. Yeah. Okay, yeah. So do you have any questions on the 3? Any of the 3? So when there's a sharp corner or a kink, when the function is continuous at the point, or if we can see a vertical tangent there, for each of these 3 cases, the function is not differentiable, right? So this is just illustrating, I think this is illustrating the vertical tangent one, right? So say you have this point A here. If you track the tangent line, and you see that as you get close to the A, this one is a vertical tangent, right? This is a vertical tangent line at that A, right? So if you see something like so, then that means that the function is not going to be differentiable at the A. And another one is this one, which is similar to what I graphed earlier on. So if you have this feature, and then at A, you see that there'll be a vertical tangent, then the function will not be differentiable at the A, right? So putting everything together is on this slide. But do you need time on this one? Okay, so there's the 3 slides that summarizes the 3 possibilities where the function is not differentiable. So the first one is if there's a sharp point, right, or a corner or a kink. And then this one is if there's discontinuity. And then this one is if there's a vertical tangent. So for these 3, the function is not differentiable there. Please, any questions on this? So just definition. Anybody needs time here? Okay. Now, we've been talking about the first derivative, right, which is the slope of the tangent at a point, right? But it turns out that when you get the f prime of x, then you have a new function, right? If you get f prime of x, it's a new function by itself. So you can also consider that function and then get the derivative of that function. So when you do something like that, then you are trying to move towards higher derivative. So it's kind of like you've differentiated the initial function twice, right? And you can do more. You can even do like 3 times 4 and so on and so forth. So that's what higher derivatives is about, right? So for higher derivatives, if a function is differentiable, right, then its derivative f prime is also a function, right? So if you can differentiate the f, then f prime is also a function. Now, f prime can also have a derivative of its own, and this is called a second derivative. So they call it f prime prime, right? F prime prime. Okay, so that's the second derivative. Now, in Leibniz notation, the second derivative is just, you know that this is the first derivative, this f prime. So if you want the derivative of the first derivative, it's just attaching the differentiation operator to the f prime. So that's why you have d over dx and then of what? dy over dx. And that'll give us d squared y over dx squared, right? So that's the notation. So this is the second derivative. So the second derivative means differentiate the first function, the f of s twice, or differentiate the f prime once. And you have to always go through f prime to get to f prime prime, right? Because it's a process. So f prime is obtained from f, and f prime prime is obtained from f prime, and so on and so forth. Please, are you okay on this? Just notations. Any questions? Okay, then let's move on. So for this one, if f of x is equal to s cubed minus x, find and interpret f prime of x. So for this, let me do this on the whiteboard. This is example 6. And you're given f of x equal to s cubed minus x. And you have to find f prime prime and interpret. Okay, now when we get to chapter 3, we'll be using the rules. Because we are now stuck with the definition of a derivative, which no one likes to use. As you can see, 2.7 was a lot of work. For that homework, it's a lot of work because you're doing everything from first principles. But when we get to chapter 3, we'll be using the rules, right? So I'm trying to get to f prime prime. Let me cheat a little, use the rules, and then use and get f prime. Now, using the rules for f prime, it will be 3s squared minus 1, right? You can obtain this using the limit as h approaches 0 of f of s plus h minus f of x all over h. Now, this question is emphasizing on f prime prime. That's why I'm doing this. So I'm cheating at this first level. But let me do the work for the second level, right? So now, if you have f prime to be this, right? We know we have to go through f prime to get to f prime prime. So what is f prime prime going to be? Well, f prime prime is the first derivative of is the derivative of the first derivative, right? So help me out write this formula. So let me say limit as h approaches 0. Now, guys, what do you think will be here? Okay, I know h will be down here, but what will be the expression up here? Can anyone think of the expression which should be up here? Should it be f of s plus h or what? What should it be here? Up here? Anybody? What do you think? Don't forget the second derivative is the derivative of the first. So what do you think will be up here? Perfect. Thank you, Jessica. Yeah, so up here will be f prime of s plus h minus what? F prime of x. Because the f prime of x is a new function, right? It's a new function by itself. So technically, it's as if you've replaced this with like g of x. And then you are saying this is limit as h approaches 0. So if you're finding the derivative of g of x, f prime prime will be just the first derivative of g, right? So if you're finding this in terms of g of x, you just say g of s plus h minus what? G of x all over h, right? But I'm trying to write it in f. That's why I'm bringing the f prime. Please, I hope this is clear. Right? Okay, so now that means f prime prime of x is now what? Limit as h approaches 0, or what? F prime of h plus s plus h minus f prime of x all over h. So let's try and get f prime of s plus h. So that will be what? So for f prime of s plus h, we have f prime of x. So if you want f prime of s plus h, it's just plug in the s plus h into the x, right? So we get s plus h squared minus 1. So that'll give you 3s squared plus 2xh plus h squared, and then minus 1. So that'll give us 3s squared plus 6sh plus 3h squared minus 1, right? And then we have f prime of x already given. That's 3s squared minus 1. So if you want f prime of x plus h minus f prime of x, then that's just going to be, let's see, the 3s squared and the minus 1 will cancel out here. So that'll give us 6sh plus 3h squared, right? So let's get back to the second derivative. So f prime prime will be what? Limit as h approaches 0 of this 6sh plus 3h squared all over h. So you can cancel out a 0. So you can cancel out an h. So that gives us 6s plus 3h. And then since you are taking the limit as h approaches 0, you plug 0 for h. So finally you get 6x. Please, are we clear on this? Okay. So this is f prime of x is 6x. Now, let's look at the interpretation. Now, don't forget that the f prime of x is the slope of the tangent at x on a function f. The interpretation is no different when you get to f prime prime. F prime prime will be what? The slope at x on a function f prime. That's all. So you always relate it one step before it, right? So f prime prime will be the slope of the tangent at what? At x of a function f prime of x. So that would be the interpretation. Please, any questions here? I hope you're okay. Anybody needs time here? Anytime, okay, okay. Let me give it a sec. Okay, perfect. So now let me go here. So this is just going to give us the notes, right? You already done this. The notes even use the shortcut. No one likes to use the rules. The rules are too long. The definition is very long. Okay, so this is just showing us a graph of f prime, f prime, f prime prime, f prime, and f. Okay, and then you see, we can interpret f prime prime at the slope of the curve, what? F prime at the point x, f prime of x, right? So yeah, that's all. Okay, yeah. Now, please, any questions here? Any questions on the solution, the example 6? Okay, then let's move on to some kinematics. So we are familiar with acceleration. For those who look at a lot of physics majors, right? You encounter acceleration, velocity, and position. And the question is, what's the relationship between these three kinematic functions, right? So if you have a position function s given as s of t, it turns out that the velocity is the first derivative of the position function. So v of t is s prime of t, right? So the velocity at time t, the instantaneous velocity at time t is just the derivative of the position function, right? So that's ds over dt. Okay, anybody needs time here? So that's for velocity. Now let's look at the relationship with acceleration. Now acceleration is also the derivative of the velocity, right? Acceleration at time t is just the derivative of the velocity. So we already know that the velocity is the derivative of the position. So that means relating acceleration to the position function. Acceleration function is the second derivative of the position function. So if you differentiate s once, you get velocity. If you differentiate it another step, you get acceleration, right? So that's the connection. So a is just the derivative of the velocity or the second derivative of the position function, right? So just note these. So maybe if you encounter questions like this and it's asking about acceleration, you know how to obtain the function. Yeah. Okay. Definitions and more definitions. Any questions here? Anybody needs time writing these things? Okay. Now, it turns out that we can also have like we only talked about second derivative, right? But you can also have like higher derivatives. You can be asked to find like the third derivative. So the third derivative is f prime prime prime, right? So 3 primes, right? So the third derivative will just be the first derivative of the second derivative, right? So just differentiate the second derivative one more time and you get a third derivative. So it goes on and on and on. So you have f prime prime prime, right? F prime 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 3 times. So the f prime 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 is the notation is y with 3 primes here, or the f prime 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 of x. And then that's just the d over dx of what? The second derivative. You can get it what we need to do, right? Multiple times. Oh yeah, so please don't worry about like the higher derivatives using the definition of a derivative. The definition of the derivative is just the mother of all the formulas, but we don't use it, right? In practical terms, no one likes to use this thing, right? This is the mother. That's why we acknowledge this formula, but we don't use it in real, like in the real world. We know that we are going to generate, in chapter 3, we're going to generate rules using this definition so that we get shortcuts to get them. So that's what we have to master. So if the question is going to ask you about y prime prime, it will be just wicked to give you like a function and ask you to find the f prime prime using the definition of a derivative. No, that's no way, right? So if you're going to be asked this, you use the rules, which we'll talk about in chapter 3, right? Okay. Perfect. You're welcome. So the notation is y prime prime prime, which is the same as f prime prime prime, or this. So it's just the differentiation operator attached to the second derivative. And then that's d cube y over ds cube. Now, as I said, we can do 4, but it's a little bit of a mouthful. When you go like the 4 is f prime 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 prime, or the 5 f prime 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 prime, 6 f prime prime. No. At some point, you have to end, right? Maybe let's find a convenient way of writing it. So when you get to the 4, instead of saying f prime 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 prime, we denote it by something like an exponent with 4 in parentheses, like so. So when you see this symbol, it means the fourth derivative, right? So instead of the prime, and so on, right? So the nth derivative, so in general term, the nth derivative is denoted by this. So apart from 1, 2, and 3, which go with the primes, for any higher derivative, they just use this notation. So if you want to differentiate something 100 times, you see it like so, either like so, right? And so on, and that's it. Okay, please, any questions here? So that's the notation, how you're going to see it. Anybody needs time here? Okay. Then let me end. This was a lot of definitions. Now this is setting us up for chapter 3. And now we are finally here, right? We are here, chapter 3.1. We are going to look at the rules. Some minutes, but maybe you can cover something small. So I'm showing the 3.1. If you can't see, do let me know. So finally, we are here, differentiation rules. Now, this chapter is very, very important. Even if you don't learn anything, the rules are the takeaway from differentiation. It's proof that you've taken a calculus class, right? So let's start with differentiation rules, right? So 3.1, we are going to start with polynomials and exponential functions. Okay, so let's look at the simplest polynomial function we can get, which is the constant. The constant. So suppose you have f of x equal to c, right? Then what is f prime of x? Now, to see what f prime of s is, you can use the mother of all formulas. F prime of s is equal to limit as h approaches 0, f of s plus h minus f of s all over h. You can use that, or you can just look at this, right? If you have a constant c, then it's just a horizontal line. Now, what is the slope of the tangent on a horizontal line, right? For any point on this, for any point here, you see that the slope of the tangent is going to be flat. So the slope is 0. So that leads to the conclusion that the derivative of x of a constant, the derivative of a constant, f of x equal to c is just 0, right? Or you can use the formula, as I was saying, the formal proof. Let me see, is it time? Yeah, almost. Okay, so for the formal proof, if you have f prime of s, what's the definition? It's given by so, right? Yeah, it's given by so, right? So what is f of s plus h? If f of s is equal to c, then no matter what x is, you will still get c. So f of s plus h is c, and f of s is c. So c minus c is 0 over h, which will be 0, and the limit of a constant is a constant. So either way, either the graph here or this formal rule, we end with this rule. So that's the first rule. So the derivative of say 2 is 0. The derivative of 100 is 0. The derivative of pi is 0. The derivative of a constant is 0. So that's where we end today. And next time, tomorrow, I'll talk briefly about this because it was the last thing we did, and then we look at other rules. So have a nice weekend. If you see anything on your exam, please feel free to let me know, right, as soon as possible. And then if you have any questions too, do let me know, right? Feel free to send me anything. Okay. And then that's all for today. Thank you. See you on Monday.
Thank you.
You're welcome.